Hello. Today I want to talk a bit about one of the new Houdini 19.5 side effects labs node called Spectral feature transfer. We'll go through sort of a prototype of how that node is built, and just show you the basic idea of how to transfer certain spectrums of certain frequency spectrum of details from one area to the other area, and how that's applied to clean up photogrammetry results. So here you can see that this is sort of the problematic area that we need to fix. This region of our scan result is extremely noisy and it has very bad topology. So to fix that, there's no easy way to fix it using a traditional delete and patch hole sort of methods. So we have to go very aggressive using volume conversion and converting back to polygon and smooth it. The result is that we fixed all the bad topology. However, we also lost all the detail that we want. So in order to get the detail back, we can sample some of these nice details from a different region and reapply here. And this is the result of the reapplication of the high frequency detail. As you can see that we retain the low frequency detail, the large, kind of smooth and large bumps and valleys that we have already here. We just need to add the additional, the sort of naturalistic look of the small details back to here. So here's another swipe between the previous problem and the fixed version. We have another video. This is part of the launch video, show you the process in individual steps. So here's the before, and this is the after, and this is the before and close up. First step is that we'll turn that into, it's a little bit hard to step through this. I'm just going to let the video play and explain what's going on. So we first turn the terrible geometry into point cloud and using metaboard to scatter onto the point cloud. That'll create a sort of a smooth merged geometry. Then we convert that smoothed out geometry into VDB volume. Then we can further smooth it. Then the VDB volume will be converted back into geometry. Then once we get to that step, I'll pause here. So what this is doing is, after the conversion from VDB, the geometry is quite is a lot fatter than the original geometry. So we can recast the fat geometry back into the original geometry, resulting in this sort of low poly look. That's because when you do recast, a lot of the points will be cast onto the same target location and creating this sort of stretched tint look. We can fix that by just apply smoothing on this again. So it will result in this kind of shape. Now the surface of the new converted geometry is much closer to the original surface. Now the video is a bit glitchy, but you can see there is a background area we selected as sort of the source location of our transfer. And here you can see the transfer kind of acts like a copy clone stamp, where each of these pin indicates a location of where the kind of sample came from, and this is sort of where the sample is transferred to. So at the beginning, it's just each of these circular stamps, but once they accumulate, they will be able to cover this whole area. The reason that we're doing this kind of stamping because the target area and the source area has no matching shape. So we can't really just grab a giant patch and apply over here. It's rather like we're building this up from individual samples. And each of these samples has to fall off so that they don't create any harsh blending edges that you can visibly see. So over many iterations, you can see now the result is much cleaner. And we do a final version where we blend the color of the original thing with the color that's transferred from all these samples, resulting in this sort of much cleaner look. And this is just the gray version. And apologize for the video clip glitching when I try to play it back while pausing. But as you can see, this is the area where the sim was. And if I leave my cursor over here, you can see it's pretty seamless here. And there's the other one over there. So that's a result. Now we're gonna start with an easy example to show you what the basic concept is like. The idea of transferring certain spectrum feature is that when you have sort of kind of information built from multiple levels of frequency, and those frequencies can be isolated, then extracted and applied. So let's apply some mountain nodes to this grid. Let me just up the grid resolution a bit first, so we have something to work with. Now add a mountain node. For this one, I want to use this to represent a low frequency, so I'm going to turn off fractal, so it's a bit smoother. I'm going to increase the element size to maybe 2 and increase the amplitude to maybe 0.5 is good. So this is our low frequency detail, and we can drop down another mountain node to add high frequency detail. So here, this is not very immediately obvious, but there's an issue when we just do things directly like this. The mountain node or the new attribute noise node, it would deform based on the point normal. So the point normal over here is still pointing upwards, but after the first mountain, the point normals might not be pointing exactly up anymore. It might be pointing sideways. So when that happens, we have actually you can see when we have a certain level of noise, it will start to deform sideways. And I don't want that. I just want it to deform upward. So we can create a normal between them just to reset the normal to point upwards. So I set this to n. Float, that's cool. Point size, the attribute size will be 3, and it can set this to normal. The value we want is 1. Now it's better. Now it goes up. Now what we want to do is to extract the high frequency noise, but I don't care about the low frequency one, because let's create a target geometry. So the target geometry, we're just gonna transform this node to the side so we can see better. So this will be our target geometry, and the target geometry will have some noise too, but not the same as the previous one. So this will be our original, and let's say target geometry has a different, sorry, not that one, this offset. Select this and press W will give you a solid template. Now, as you can see, the low frequency detail is different. Just pick a different offset. Maybe like this, okay. I just want these fine-grained detail to be transferred to a different low frequency detail. So this has to do with the kind of the decay rate of different frequencies when you apply diffusion or smoothing. High frequency detail basically decays faster. We can use something like smooth to achieve that result. So if we smooth this, here's the filter quality and the strength. Strength is like how strong the thing goes away, and the filter is the higher the filter, the more detail is retained. The lower the filter, it becomes more smooth. This is actually tricking your eye because we updated the position, we did not really update the normal. So if I drop down another normal, you will see it's much smoother. So now what we're going to do is to calculate the delta between the two. So we can drop down attribute render node, and for the first branch we'll do the smooth result, And for the second branch, we'll do the original result. And we'll also copy another, actually, that's fine. We don't need to do the normal. So what we're going to say here is just v at delta equals v as in vector. We want to subtract the delta from the more noisy one, which will be the original. So we can refer to that from the first input using the point attribute functions. It will be point 1 as in index 0, 1, that's the second input. And the attribute we're interested in sampling is p, and the point that we currently want to use to sample that attribute is just the current point number, so ptnum. So this will give us the position of the high frequency noise one, but we want to subtract that by the smoothed out one, which will come in as just a p attribute, because that's the first branch, as also this node where this node is clicking on, so you can just refer to that as p. So this would give us the delta. As you can see, it has delta in the y component. So now we just need to apply the delta to the right side. Because this is just a simple example, the basic concept is quite straightforward. There are additional things we need to work on for the photogrammetry example you saw earlier, because of a reason I'm going to explain. So if I take this to the first input and this to the second input, and click on this, just going to do at p equal at p plus 0.1, the attribute now is delta that we want, and again ptnum. Let me move a normal over here. Now, as you can see, we've successfully transferred the detail over. And if we change the filter quality, it changes what level of detail we're transferring, because the smoother you get, the bigger the delta, the more noise that you're transferring over, and vice versa. Okay, that's the basic example. Now, here the transfer, even though we have two grids here, they have the same point counts. Now let's see what happens if this grid has more point counts. Let's say if we do 2 of these, this one will translate once more. Let's say if our target looks like this, and we transfer. As you can see that the right one, it doesn't get any result, because the mapping we established is was basically banking on the fact that the ptnum on this side and ptnum on this side is the same, but since this side has twice as many point numbers, so it only was able to establish the mapping up to the point where the ptnum can find its equivalence on the target side. After that, there's nothing being done. So this is not what we want. We know that in our example, the source area and the target areas are quite different. And also they don't have this sort of spatial relationship where they're laid out in the same way. So if I change something else again, you'll see there's also a problem. So let's say if I temporarily just disable this, but let's rearrange the point order. Here we can visualize the point order. Let's say random. Okay. Now you can see this result is not what we want. This is the correct one, this is random, because the whole relationship is based on ptnum, and if ptnum is random, then you just destroy the spatial continuity of the high frequency noise you have. So for our version, what we need to do is sort of a copy stamp operation. The idea is to create all those sample points. Let me just jump over there so we can see it more intuitively. Let's look at our source. This is our source geometry. And this is our target geometry. Smooth. So idea is to create locations to sample this from, and for each stamp we're going to use a circle, and we instead of using point number matching, we will physically kind of move that circle over to a certain area above this area, above the target, then project that circle down so that it create a proximity matching relationship. Then we're just going to transfer the detail based on proximity. So to do that, let's create the anchor points for the target area first. We want to scatter points on this side, and we want basically 200 samples. And if you increase the relaxing duration, it will make sure that the samples are spread out as evenly as possible. Then we'll give it a little bit of add up attribute so that we know which way is up. Now this serves as a target anchors. Now we need to establish the source anchors so that they have a one-to-one relationship. So source anchors will also have 200 points. But before we just directly scatter 200 points onto this, we can think about it for a second and realize that for the source anchors, if we want to move a circle over to the target side, we don't really exactly want the circle to be cropped, because if it's too close to the edge or something like that. In this example, this is not part of the tool. It's just sort of a quick and dirty example here as a showcase of how the technique works underneath. I want to crop the boundary so that the whatever point we're going to scatter is sufficiently away from the boundary. There are multiple ways to do this. I think I did earlier in a kind of silly way. So we can start with a line and use a cylinder generator to create a cylinder like this. Set a radius of 1 and a few tweaks on the U segment, and add an end cap and triangulated it. Then triangulate everything else. Then use this sort of as a thing to scatter. So on this side, we first selected the edge. Grouped all the edge points. If you blast everything else that's not the edge points, you end up with something like this. You will see there are some triangles still left in here. We don't need that, we just need the points. So you can extract all points, that gets rid of the triangles. Then we use a random selection, set it to periodic constant intervals. That what this will say is that it was going to select a point and skip the next 50 points. So this is the result before and after. So try to evenly reduce the number of points that we have. Then we give it normal. This is useful to orient the scatter. So orient the property point. Now we have all these points over here, just a bunch of cylinders sat together. It might be tempting to do a Boolean operation, but that will actually be kind of terrible, because this is lots of faces inside. We don't need that. We just need the shell of it. So the standard operation to turn something with lots of inside faces into just a shell is to do it through volume conversion. So here we'll convert this to VDB. Now we actually don't even need to convert it back to geometry to create the Boolean. We can use the group keep in bounding region and bounding volume parameter to select all the points that's in the bounding volume, like so. Then we're just going to delete them, because if scattering any of those areas, I'll be too close to the border. Now this is sort of a trimmed off version of the source. then I scatter points on them with the with a lot of iteration. So that's going to be our source anchor, 200 points on this side, and target anchor on that side, 200 points. Now we need to prep the geometry a bit more. So for the target, we want to transfer color as well as the position delta. So because we need to build up the color, so we're going to build it up from black instead of white. So because it's black, you can keep adding color to it. The other thing we're going to do is to prep the source so that it has the delta attribute we want. In this example, I'm doing it slightly differently. Instead of smoothing out P, we can smooth out any attribute. That's sort of the point. Use spectral transfer of any attribute, not necessarily just the position. Here we create this height attribute based on the height of the P. Then we smooth out this attribute with a very strong strength. Then we modify the height based on the smoothed out result. Give it a normal update, so now it's smooth. Here we subtract the height difference between the two. This is just a shorter expression to say grab the P attribute from the second input. Tell the expression that it's a vector attribute because this point function can grab any type of attribute. So in this case, it's easier to append this square bracket 1, which means to grab the second component of vector, because you're using that, so you need to say this is a vector. So that's why you have a point vector and this, which basically gives you the P at Y from this branch. Then subtract that, you get the delta. You don't see it, but it's here. If you check the geometry spreadsheet, the delta value is there. Then we also don't need the faces, we just need the points because we're transferring data based on points. So let's just delete everything except the points to keep the memory down a bit. Now, the final bit of prep we need to do is on the target geometry. We've already reset the color, but we need to create the attributes that we need to work with. So here we have the delta. The delta will be added each time from a stamp onto the geometry. Then there is which is that cumulative delta. It would keep adding because the stamps will overlap each other. So we'll add the delta first, then we'll try to take into account of the stamp weight. So we create a weight attribute, which also is responsible for handling the fall off from the center of that stamp to the outer edge of the stamp. So you kind of have a soft stamp. They also accumulate the weight. So you can see it's basically two pairs of attribute, delta weight, accumulated delta, and accumulated weight. Then we have this loop here. This is a feedback loop. So we're going to feedback how many times. We feedback the number of times as the stamps we have, so 200. So in each iteration, we're going to take one step. And right now, I'm just going to do a single pass so you can see what happens in a single operation, in a single iteration. So first, we need to grab a single point from each branch. So we're using the blast node, and you can add spare input. And it gives you this thing over here with an empty field. Then you can drag the block metadata node into that. So it'll be easier for you to fetch the detail attribute from that node by just using the -1 expression, because -1 refers to spare input 0 and spare input 1 will just go in the other direction, will be -2 and so on. So here we'll just group takes a string, so that's why you have a backtick. It's going to evaluate this expression into a string. So this is just saying iteration number 0, because we're just dealing with point number here. So point number 0 to 199 is the same as the iteration number 0 to 199. Same for the other one. So here is the source point, and this is the target point it's going to go to. So let's first isolate the source patch. There it is. Let me template the geometry here so you can see what's happening exactly. So let's do it one step by step. Let me disable some of the position things first and look at the source patch as it was originally at. So this is a target and this is our source here. So the source point is in the center here. Then we kind of basically say check the location of the source point. This is the location, and check it against all the points. So this node runs on all the source geometry. So it's telling all the points in the source geometry to compare itself with the center location and see what's the distance. And if the distance is greater than the radius that we set, and this sort of the sample radius here, then we discard them. But if it's within this radius, we're gonna do something to create that gradient. The gradient we're doing is that when we create the gradient, we just want it to be like a kind of a 2D gradient here for this example. So we don't want to take into account the difference in y. So we can we're borrowing the sources y, so that when we do the comparison between the coplanar p and the actual source p, we're only checking the distance differences in the x and z direction. So we get a new radius, and this new radius will be turned into a normalized range because we want to work with a ramp, and this ramp expects 0 to 1 in the input direction. So this is our ramp. Instead of saying if this is the center of the sample and the fall off goes into that, it's solid and kind of start to fall off halfway through. This is the distance, and this is the maximum possible distance. So if you divide the current distance, like for instance, like this distance for that point, by the current distance, the current radius max, it gives you this point's relative distance in the 0 to 1 range. Then we just assign the weight based on that fall off ramp using the radius. So if I do this, you should see that's what the weight looks like for visualization. Now we do need to establish the mapping relationship, so we need to move that point over to this side. So the first thing we do is to take into account of the mapping. Taking into account the delta difference between the target point over there and the source point over there. If we just apply that to every point inside the circle, that moves the whole circle over to this side. But now it's sort of like sitting somewhere and penetrating things in a weird way. We want to do a clear downward casting. So I'm just going to move everything up by maybe a bit too much. Maybe we don't need to move it up by 20 meters, but I did, it doesn't matter. Then we're going to do a raycast downwards against the target, because what's running through the loop is the target geometry as a whole. So this branch grabs the target as a collision geometry, and here we set it, the direction as a vector, and this the vector direction is downward direction. So that projected our source patch onto the target patch. Once it's projected, we could do attribute transfer with very little, pretty close distance to do the attribute transfer. So here we're transferring over the delta, the weight, and the city. Weight and city is a bit obvious. We want to grab the color, as you can see here, and we want to grab the delta. But the weight is so that we can check for each location in the target how much it has been overstamped. So let's say if no other stamp ever touched this point, then the value currently transferred will be used as a final value. But let's say this point is also touched by 2 other stamps, and depending on the fall off weight added together from all the stamps that ever touch this point, we'll get a weight that's not 1, that might be higher, might be lower, because it depends on, like, if this border have a point of 0.2 and 3 stamps touch that point, and neither of them has high enough weight, the weight will be below 1, but it will also be higher than 1. The point is, you divide your transfer data by whatever weight that has been accumulated. That basically give you a result that's as if the weight has been 1. So that kind of cancel out all the overlapping areas and give you a smooth result at the end. This concept is relatively simple. So here you can see when we do the accumulation, we just add the delta to the accumulated one plus the weight. So this weight is responsible for the fall off within this particular circular stamp. Same thing you see here. We have a color. This color is pretty much, you can name it accum color to its accumulative color. Structure-wise, it's the same. You take the actual color and apply the weight. Then we just accumulate the weight. So maybe this code should be better organized like this. It'll be makes a bit more sense. So accumulate the weight, and the color will just be accumulated color. Then delete the target group. We don't need that at the end of each iteration, and that's the iteration number 1. Now you can see here. You don't see the weight here because weight currently is not applied to the color yet. But if I run here, you see a bit more, obviously. But ultimately, we're gonna see the result of everything. So I'm just gonna pause the video a little bit and finish the transfer of all 200 points and come back. Now the transfer is done. What I did I turned off the single pass and we did 200 iterations. It's smooth right now because your eye is tricking you because the normal hasn't been updated yet. No, your eye is not tricking you. Your eye is telling you the truth, but the normal is tricking you. So here what we do is, main part is this one. That's just ignoring some like unshared points. So here you can see if the cumulative weight is greater than 0, means that there's some data there. Also to avoid that dividing by 0, what we're gonna do is we're gonna modify the py attribute by taking the cumulative delta and divide it by the cumulative weight and give us the expected deformation we want. Here I added a rather arbitrary multiplier just to give a bit of more intensity to the detail. Reason being, we are overstamping quite a lot in this case. So when you're overstamping and you're smoothed out by dividing by the weight, it kind of blur everything a little bit. So to counteract the blurring effect and give it a little bit booster. Same for the color. So for the color, just the cumulative color divided by the weight. So if I did that and I hit update normal, now you can see this is a final result compared to the original geometry that's colorless and without any detail. And we got all those nice little details from the sourced patch. So this is sort of the underlying principle of how the tool works. I'll give you a general idea. Ultimately, the tool that's going to come out, the Spectral feature transfer, will have a bit more different built to be more robust, to be able to target things. That's not just a top-down plane-to-plane transfer. It's going to be able to handle other kind of shapes, other kind of facings. So like from like a surface of a sphere to a cube, or from cylinder to ground, anything. But this is easier to explain what's happening and what's the basic idea behind it. Once again, is the decay rate of different frequencies when you diffuse or smooth data. The higher frequency detail will decay faster, so if you compare the delta between the two, you'll be able to isolate the information. Then you can move it to a different place.